Hello, guys. Welcome to another episode of Cuda Education. So today we are going down the we're going down the road of really trying to understand textures and figure out what's going on, how it all works, and you know how we could understand and process all things related to textured materials. Okay, so this is Clean Slate 3.0 series. So the 3.1, 3.2, 3.3, the 3.0 series, right? Clean Slate 3.0 series. We are we're now developing this whole textured material discussion and really getting our hands involved in all of that thing. So first of all, I want to, in order for us to understand textures, one thing that keeps coming up, one concept that keeps coming up is this concept of a heap. Okay, and it's something that deals with memory management, memory processing, all of that stuff. So for this video, let us just kind of go through the motions of discussing the heap. Okay, so let's just go. So what is a heap and why is it relevant in this discussion? When I say relevant in this discussion, I'm talking about in the whole textured materials texture discussion. So a heap here means a metal resource heap, MTL heap. It's one big pre-allocated block of GPU memory that you carve smaller resources, textures, buffers out of yourself instead of asking metal to allocate each one independently. So just think of it as like, maybe, you have a whole pizza pie, but then you carve out a slice and you block that slice off as, as a personal heap. Now, inside of that slice, you're gonna have different, you might have further sub allocations or subsections that deal with specific things. So we might have a big heap, and then we have, as part of that heap, a smaller sub allocation of things dealing with texture and texture related stuff. Okay, so that's what this thing is. Now, doing it that way, where you carve out a pre-allocated block of GPU memory, doing it that way is generally more efficient. It's you don't have scattershot allocations across your whole memory space. The similar things or things that are regularly accessed together can be grouped together, more closely packed together, things of that nature. So the two ways to allocate GPU memory. Now we're going to discuss without the heap and with a heap. So without a heap, we have ID, MTL, texture, text, device, new texture with descriptor, and then descriptor. Metal finds and reserves memory. So this is without a heap. Every texture is its own standalone allocation. Metal manages each one's memory and residency separately. Okay, now with a heap, we have ID MTL heap, and then we have heap equals device new heap with descriptor, heap descriptor. One big block example texture heap size. So we'll have one big block chunk of memory that's sectioned off. We'll call this heap, and maybe the size of it is texture heap size. So all of our texture needs, I would assume, memory needs, will be represented in sort of the size of all of our memory needs would be texture heap size, right? This is kind of like a constant or something. And then we then have ID MTL texture text equals heap. So this heap variable, same here. But then new texture with descriptor, right? Sub-allocated inside that block. So remember I said we had our pizza slice of the pie, and then inside of that slice we have sub-allocated block that deals with our texture needs, or this specific texture need, however you want to look at it, right? So with a heap, we have these two things going on. You reserve a large slab once, that's this guy up here. Then sub-allocate many textures inside it. That's exactly what APL Texture Manager does. Note its property read-only ID MTL heap MTL heap. So APL texture manager header file line 49, and the heap size texture heap size argument passed when the renderer creates it. So let us deep dive into this for a second. So we're gonna go to APL texture manager.h. That's this guy right here, and we want to go to line 49. So that's this guy. So notice that we have add property heap, and then we have it's a read-only property, okay? And then do we have okay, so texture heap size is not part of that discussion, but we will get to that. Right, so 49, and the texture heap size argument passed when the renderer creates it. All right, I don't see the. So let's go to. No, not here. Okay. Okay, so yeah, that's something that we'll have to. So texture heap size argument passed when the renderer creates it. Okay, so so I guess we'll stumble on this at some point, okay? But we understand here that we have heap, MTL heap, and we have our big block of memory here, and then we have a sub-allocated inside of that block because we're using this variable here. And then when we go to the header file, we see we have add property read only not null ID MTL heap, right? So we do have heap here, and right, which was created here, okay? Why it's relevant to the texture discussion. The bistro scene has hundreds of textures, every wall, window, prop material. Two concrete payoffs drove the heap choice, and both showed up in the code you just read. So this is our application here, and we see a lot is going on here, okay? A lot is going on here. So the bistro scene has hundreds of textures, every wall, window, prop material. Two concrete payoffs drove the heap choice, and both show up in the code you just read. Residency is the big one. The GPU will only read a resource if it's marked resident, guaranteed present in memory, for that command encoder. With individual textures, you have to call use resource for each one, every frame, hundreds of calls. With a heap, one call covers everything inside of it. So texture manager, make resident for encoder, okay? So we have our underscore texture manager, make resident for encoder. APL renderer, line 291. One call, all textures. So let's go to APL, line 291. And it is make all textures in the heap accessible to the shader. So this guy right here, okay? So we're gonna have to go right. So with one heap, one call with a heap, one call covers everything inside of it. So we have our we have our call right here. That single line which uses use heap under the hood is why the per submesh loop can just bind a texture and draw without worrying about whether the GPU can actually see it. This is the direct reason a heap is used in this renderer. So again, it's getting back at a level of efficiency. Make all textures in the heap accessible to the shader. Okay, so we are in AAPL renderer, draw in MTK, as we could see here and here. And 291, make resident for the encoder. So again, guys, let's just, residency is the big one. One GPU, the GPU will only read a resource if it's marked resident. Guaranteed present in memory for that command encoder. With individual textures, you have to call use resource for each one every frame, hundreds of calls. With a heap, one call covers everything inside of it. Okay, so that's the first reason why it's relevant to this discussion. Residency is the big one. The second one, cheaper, faster allocation. Reserving one big block up front and sub-allocating is much faster than hundreds of separate driver allocations. And it packs textures tightly, less wasted memory, better locality. It also makes streaming practical. You can evict a texture and drop a high-res version into the same heap space later. The use texture streaming path in the texture manager builds on this exactly, but let's not worry about that right now. Okay, so cheaper, faster allocation. Reserving one big block upfront and sub-allocating is much faster than hundreds of separate driver allocations. Now, I want to kind of harp on this for a second. Remember, we have hardware, we have software, and drivers are somewhere in between the two to make sure that the software and the hardware dance properly together. You generally don't want separate driver allocations because just the administration and the management of it is a royal nightmare, and you don't want that. So you don't want separate driver allocations. You want things to be done in one big block. You want it to be done closely together and tightly packed. And it packs tightly together. So you want the memory to be tightly packed together. And also better locality. So, the next thing you need is literally right beside the first thing you need. It's not in some distant random location elsewhere. It's literally right beside each other, right? We're always in computer graphics and in processing, we're always looking for efficiency and less use of energy and time and all that stuff. So less wasted memory, better locality. It makes streaming practical. You can evict a texture and drop a high-res version into the same heap space later. All right, we're not necessarily going to get into that right here, but cheaper, faster allocation. So these are the two reasons why the heap approach is used. I think I selected some code. So encoder, draw, index primitives, what have you. Okay. But anyway, let's stop here, guys, and let's not get too involved. But basically, we kind of understand the idea of a heap, and we will develop this idea further going forward. This is Cuda Education, guys. You know what to do with the channel and all that stuff. Have a great day.